Today we have Yairon Cid-Ruiz telling us about log-concavity of polynomials arising from equivariant cohomology.
Okay, thank you very much for the invitation. It's a really great honor to speak in this magical place. I'm going to talk about this joint work with Jupon Lee and Jacob Matherney. And my talk will be divided in three parts. So in the first part, I will do a recap on this behavior of log-concavity of cohomological classes. My main interest is if you have a subvariety inside product of projective spaces, and I will basically be presenting works of people from this audience, more or less. Then my interest in this talk is let's see whether we can find some log-concavity and the torus-equivariant cohomological classes of varieties inside the space of matrices. And then, time permitting, I will try to present a generic version of Macaulay's inverse system that can be applied to cohomology rings. Okay, so let's do the short recap. So suppose that you have X biprojective closed scheme, let's say over C, of dimension D. Then we have this notion of multi degrees that goes back to Van der Waerden in 1929, that for all I plus j equal to the dimension, then we have this by degrees, depending, of course, in the product of projective spaces, that is just the following intersection number. So 1, 3, 0, 1, j, and the class of x. This is always bigger or equal than 0. And then the first question that you have is a positivity question of when these numbers are going to be positive. And the first instance, or the first person that I can find in the literature that considered this positivity question was the theorem of Chung in 2001 that says that if x is irreducible or arithmetically cohomology, this means that the coordinate ring of x is a cohomology ring. Then he showed that the following sequence, A0, A1, all the way until AD, where AI is this multi-degree, has no intermediate zeros. Yeah, and this means that if I is smaller than j, is smaller than k, and ai times ak is different from 0, then aj is different from 0. Okay.
So by the coordinate ring, you mean like the bi-graded?
The bi-graded coordinate ring. So x in this case will be the bi-approach of some standard bi-graded algebra. Then the next instance that I can find, maybe I can say that the motivation of this sort of result comes from a slightly more algebraic area. So we have this notion of mixed multiplicities that was developed by Tessier, Ruiz, many other people, that if you have I, an ideal in an Euclidean local ring, then we have these numbers, EI, I. Okay, and it was known for a long time. So these mixed multiplicities are just the bi-degrees of some bi-projective scheme. And it was long known that for a long time that these numbers were between the height of the ideal and something called the analytic spread. And we knew that at the height and the ideal, they typically were non-zero. And then was an open question for some time whether in the middle, those guys were not going to be zero. And this was settled by this result of Schum. Then the next result that I can find in this direction is the first paper of Yairon Huh in 2012, and he says that if X inside this product of projective space is a subvariety, so an integral closed scheme, then this sequence, as I define it there, has a no intermediate zeros, it is a log-concave. Okay.
In the motivation, what is we have EI? What is that? Sorry, what do you mean?
The motivation for this result of Schum, if you have an ideal in an Euclidean local ring, then you can define something called a mixed multiplicity of the ideal with respect to the relevant ideal. And let me say that actually this notion of mixed multiplicities played an important role in that paper of Yairon Huh. Okay, so we have that. So then I want to draw the difference here. So you have irreducible and arithmetically cohomology, and in the case of this result of Yairon Huh, you only have it for irreducible. So a priori, I think there should be so he gets no intermediate zeros, and it is log concave, but motivated by Schum's result. I think it would be nice to attack the question. Okay, I'm going. So the next result that I have that we can find there also is by Brändén and Huh in 2020, that if X is reducible and you have a sequence of Neff line bundles, Neff divisors maybe better, then they show that the volume polynomial of X with respect to this divisor, which is H1, T1, to the way Hn, N to the dimension of that irreducible subvariety of X. This is a Lorentzian polynomial. Okay, so Lorentzian polynomials, one of the definitions is the support is convex, so the support is a polymatroid, which in the two-dimensional case here, in the biprojective case, will be just has no intermediate zero. And then the other part is that the d-2 order partial derivatives, they have a Lorentzian signature, but one of the nice properties that have Lorentzian polynomials is that they extend in a nice way this log-concavity result. Okay, so then we have this weird behavior or nice behavior that as long as you have a irreducible multiprojective or an irreducible projective variety, then you get both a nice support and log concavity. But I think it would be nice, motivated by this result of Schum, instead of assuming irreducibility, so suppose that X is not irreducible, and then what can we say about the support of the volume polynomial or the cohomological class of some variety inside product of projective spaces? Okay, so for instance, what can we say when X is just ACM? And we believe, we have checked many times that when X is ACM, the support should have the property of having a saturated Newton polytope property. We have some examples of ACM where it's not going to be an inconvex set, it's not going to be a polymatrate. Yeah. Then, so this is all part of the recap, but this question I think could be an interesting question. So when X is connected in dimension 1, so by Harshon's connectedness theorem, whenever you have something ACM, it is connected in codimension 1. And actually this result of Schum actually holds valid when you just put that X is connected in codimension 1. Okay, and then the other question, when X is connected in codimension K. So long story short, in this recap, so whenever you have something irreducible, you have this marvelous behavior of both the support and log concavity among the coefficients. So if we already have a nice behavior for something irreducible, it would be nice to have some connectedness theorem that these cohomological classes in some way should capture the topology of the variety. Okay, so that's the whole recap that I was planning to do. Is there any question?
So sorry, so what is conjecture there? That is a polytope, the support?
The support, if X is ACM, I conjecture, let's say, that the support should be a saturated Newton polytope. We have an example where it's not inconvex, where it's not a polymatrate. Some triangulation of some sphere, blah, 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 but this is still SMP. So, I mean, the idea would be that, so we have all these amazing results. When you have irreducibility, you get both the support and log concavity of some sort. So let's study like connectedness or some topological properties of the variety. So because I only care about the support, so I can just go to the reduced scheme structure. Can we say something? It would be really nice that if X is connected in codimension 1, then can we say something about the support?
Do you have a conjecture for that? Or not yet at this point yet.
I just conjecture for X, if X is ACM,
Yeah.
I should be saturated Newton polytope. And the idea is like, I mean, each irreducible component, they're really close in this case, they're connected in codimension 1. And the support of each irreducible component is a polymatrix, so they're a super special type of polytope, no? And there's like the union of those things, I don't know. Okay. Good. So I went slightly fast with the recap because I don't know, because of the audience maybe. Yeah.
So the board on.
Oh. Okay. So I think that those questions will be interesting. So more recently, we have a nice work of Aluffi that if you have a product of projective spaces, then for any subvariety in this product of projective spaces, let P X T1 the Tn be a polynomial. So the polynomial associated to the class of X inside the child ring of this product of projective spaces, which is and then a definition by Aluffi in 2023. So he introduced this notion of covolume polynomial that can be seen as a dual notion of this notion of volume polynomial. Yeah. And he said that a polynomial in n variables is covolume if it is a limit of polynomials form alpha p the class of X, where alpha is some positive real number and X is some irreducible multiprojective variety. Okay, and what is the connection between volume and covolume polynomials? So we have this nice lemma that I will put Materne Mesaros this year has Aluffi. Well, if the polynomial is covolume, then this complement T1 the M1 all the way until Tn Mn T T1 to the -1 all the way until Tn to the -1. The normalization is Lorentzian. Okay, so these covolume polynomials automatically will have nice properties, so they will inherit in a natural way properties from Lorentzian polynomials. Aluffi gave some examples of covolume polynomials that are non-Lorentzian. So maybe I'll go here. So then our interest is that so let's go to the second part. So let's say that mat M n is a space of m by m matrices, and then we have a torus with the following action, the usual action, T g comma h dot m will be g m h minus m h to the -1 for all elements in this torus. So this is the usual type of things that you want to study when you want to study the Schubert polynomials or things like that. And so let X be some torus invariant of this space, and we want to see what can we say about the cohomology class of the torus-equivariant. So we want to study so the torus-equivariant class of such a torus as invariant subvariety inside the cohomology ring with this space matrices. So this is just a big affine space. So this is just the homology of the point that people denote by gamma t, and this will be just a polynomial ring in a bunch of variables, let's say t1 till tn, and then there's 1 till sn. Okay, so that's our goal. And the main result that I want to discuss today, so let's, just for this ease of notation, let Cx in a bunch of variables be the polynomial so representing associated to this equivariant cohomology class, and our main result with Dupont and Jacob is that these polynomials, so of course, because of the ways that I'm using here in the torus, the variables, the S variables will be typically negative, so we need to change signs. So T1 until Tm minus 1, or the one is minus Sn is the covolume polynomial. Okay.
Sorry, could you explain the definition again of covolume polynomial?
Yes. So for any irreducible multiprojective variety, you get a polynomial associated to its class inside the cohomology ring of the product of projective spaces. So this will be a homogeneous polynomial of degree equal to the codimension of the variety.
Okay.
And these polynomials by themselves, they have some really nice properties. They are inconvex, and then Aluffi said that a covolume polynomial will be a limit of classes of multiprojective varieties.
Okay.
Yeah.
Okay. And what is n?
N is inside
Sorry.
the product, the number of product of projective
There's a
space.
capital N.
Oh, normalization.
Okay.
The normalization.
Is it like dividing by the factorial?
Yeah, the factorials. Yeah, the normalization of x to the alpha will be x to the alpha factorial. Because many times a polynomial is not Lorentzian, but its normalization it is. So for instance, if you have a polymatroid, then and for each point of the polymatroid, you create the polynomial associated to that polymatroid. That guy by itself is not Lorentzian, but its normalization will be Lorentzian.
Okay.
Yeah. Yes.
So in that example, when you have a point, that's what the ring of symmetries.
So this is the cohomology ring of just one point.
Okay. But that's using lambda there, but it's not symmetric functions. It's just.
Oh, no. I'm following the notation of Anderson Fulton textbook. Yeah. I don't know if it's a standard notation. Yeah, I don't know. You can complain. Okay, so that's our goal. So we know for multi-projective varieties, we have, or even just projective variety, and you have a bunch of line bundles, you get nice polynomials. So our hope it's to create a new class where you have this log-concavity. Okay. Yeah. And there is nothing special here about the space of matrices. You can just you can get any affine space and any torus as long as you have you can divide, like you can see here the weights are positive and here the weights are negative. As long as you can have a positive part and a negative part, this theorem will hold. And let me show an example that if you do not have that property, then you will not get this kind of result. Yes. So an example. So arbitrary torus actions do not work. So let's consider just C2 and C star to the 2 with the action H1, H2 dot A1, A2 equals H1, H2 A1, and then H1, H2 to the -1, A2 for all H1, H2 inside the torus, and all A1, A2 inside C2. Okay, so and let me just consider. Let's take X, the variety given by the origin. Okay. Then, of course, X is irreducible. Of course. However, we can compute that the class in this case will be T1 plus T2, corresponding to these ways here that we have, times T1 minus, I mean, the origin is just a complete intersection, capping out by X1 and then capping out by X2, and then the cohomology class will be just the product of the weights coming the X1 and then X2, okay? And this will be equal to T1 squared minus T2 squared inside this, okay? But this polynomial has no SMP, I mean, and it's not convex. If I put here T1 and then T2, so here I have 1. So one of the monomials and the other monomial, and I'm missing the 1, 1. Okay. So not even can convex. Okay.
Sorry, like if you change the torus action just by on the matrix space, just by doubling everything, would that also produce a counter example?
No, that would be okay. You mean like something like G squared minus to the 2? That also will be okay. Yes, that's what we prove. The only constraint that we have is whether we have positive and negative at the same point. I mean, in the setting of this Knuxon and Miller stuff, it's because the Hilbert function is not finite. It's they have a name for when the Hilbert function, every graded component is finite.
So it's not about the like effective action of the torus. Like this torus action has some kernel, right?
I mean, the only issue here is that in this guy acting here, the H2, it has both positive and a negative. That's the only issue. As long as you have like a positive part and a negative part, everything will be fine. If you have like in the second component here, like you have both positive and negative, then you run with this sort of issue.
I square the action, the effect is not to square the variables, but multiply by t.
But multiply by t.
Oh, yeah,
That's precisely.
I'm sorry.
It's always linear. It's just like something a t. The C alpha, the C in your book, yeah, C sub A. Yeah. The C sub A is the AP. Yeah.
Okay.
Yes. Okay. So the only constraint that we have is we need to put a positive part and a negative part, and then everything will be fine.
So so you say this is a covolume polynomial, like,
Yes.
do you have a
We can
variety
produce,
out of the projective space?
we can produce the main part of this talk is how to produce the precise multi-projective variety.
Okay.
So we show that this after something will be the class of some, well, maybe no X, the class of some Y inside a really huge product of projective spaces. Yeah. Okay. But indeed, if arbitrary torus actions will not give you good things. So if we have I'll go now through the usual applications. If you have some permutation, we have the matrix Schubert variety or some degeneracy loci, psi space of m by n matrices, and I don't know, maybe many people contributed to this. Fulton, here, Manji, and then Nuxon, Miller. We have that the double Schubert polynomial will be equal to the torus-equivariant class of this matrix Schubert variety. Okay, so matrix Schubert varieties or the degeneracy loci were studied by Fulton. Then the equivariant versions were done by Ferrer and Rimanji and Nuxon and Miller. Am I forgetting any names? Okay. Okay. Yeah. Okay. So then a corollary will be that if you take the double Schubert polynomial and you change the sign of the variables Si, this is a covolume polynomial. Okay, and maybe the story here is slightly longer. So before with some other collaborators, with Federico Castillo, with Jonathan Montaño, two Colombian mathematicians, and Fatime Mohammadi, we show that the support is in convexity of the double Schubert polynomial, and the proof that we use here is basically more or less the same that we used there, but we were somehow laser focused just in the case of Schubert polynomials. Now we have a more general method, and I should say that all this n-convexity and actually the SMP property of many polynomials was conjectured by Monicalto, Kang, and John, and that the case of ordinary Schubert polynomials was done before by Finn, Mesaros, and Sandisier. Yeah, okay. So that's the usual applications that you would expect. So our approach is very algebraic. So we use this work of Nuxon and Miller. Whenever you are considering the torus-equivariant classes of some affine space, this can be done alternatively in terms of these multi-degree polynomials and K polynomials that you can read up from a Hilbert series. Yeah. So now I'll consider let R be the coordinate ring of this space of n by n matrices. Yeah, and we use the grading on this polynomial ring. So the degree of the variable ij. So if I want to really model the way that I'm doing it with this torus action, I should put that the degree of the variable xij should be ei minus ej inside c to the n, c to the n, where ei, the ith elementary vector, is here, ej is the ith elementary vector there, but I will delete the minus, okay? And if we have P, let's say some prime ideal, well, actually, this irreducible subvariety inside the space of matrices will be actually the vanishing of some prime where P will be a prime there and is homogeneous with respect to this gradient. Okay, and Knuxon and Miller, they define something called the K polynomial that is supposed to read the K cohomology classes and the multi-degree polynomial. Following this convention, then we will have the following proposition that this class that we want to study will be the multi-degree polynomial of R modulo P, T, and then I put negative the variables. This is basically because I changed the sign there, okay? And then why do I want to do that? Well, for starters, by some known positivity results, this multi-degree polynomial will be actually with no negative coefficients. Okay, and yeah, so now the idea is that we are given a prime ideal inside a polynomial ring with a positive grading. Yes, and as soon as, and the theorem that we will prove is that if you have any prime ideal with a positive grading, then the multi-degree polynomial will always be a covolume polynomial. Yeah, and this is of course motivated by Hartshorne's polarization. We introduce a technique called standardization. So in his thesis, Hartshorne, he showed that the Hilbert scheme is connected, and somehow one of the main techniques, or he just called it an auxiliary construction, and this auxiliary construction is nowadays called polarization. The idea is that if you have, I don't know, a non-square free monomial ideal, you can produce a square free monomial ideal now in more variables that I will do in this case. So as degree 2, then I go x1, 1, x1, 2, as degree 1 in the variable, so x1, 1, x2 comma 1, and then x2 comma 1, x2 comma 2. And it turns out that this very naive looking process respects or captures all the homological properties of this ideal. So for instance, this ideal and this ideal will have the same graded Betti numbers. And one of the main tools in this proof of the connectedness of the Hilbert scheme, so you get an ideal, you go to a Borel fixed ideal, so this is a monomial ideal. Then in those monomial ideals, he performed this polarization process. Then you get a square-free monomial ideal. So it's just an intersection of variables. And then those variables are new variables. He substitutes them back into some linear forms. And so in this process, he had something called canonical distraction, that he was able to break apart a scheme into something that was just a union of linear spaces. And by interacting that, he showed that the Hilbert scheme is connected. Okay, so the idea is that something seems that are not multiplicity free, or that has more than degree 1, you want to decompose it into something which is carefree or multiplicity free, just 1. So we want to do that same thing for the grading of the variables. Okay. And I have the grading there. Perfect. Yeah. Okay, so so the idea is that you are giving a non-standard grading and you want to create a standard grading. We say that this is standard grading when the total degree of each one of the variables is just 1. Yeah, and this grading will be the one that corresponds to product of projective spaces. Yeah. So you can do it in general for any positive grading, but let's just stay in this case. Okay, so I will define now a new polynomial ring. Yij, Cij, where I goes from 1 until n, j goes from 1 until n. So, in this polynomial ring, we use the grading that the degree of Yij will be EI, direct sum the 0 vector inside Cm, Cn, and that the degree of Cij will be 0 plus E sub j inside Cm, Cn. So notice that the Proch construction of this S will be just a product of projective spaces. Yeah. And really, the most important thing here is that the degree of Xij is equal to the degree of Yij plus the degree of Cij. Okay, which is what Harshon does here. So something of degree 2, something of degree 3. Yeah. So for some ideal inside R, we say in homogeneous with respect to that grading, we say that J, so the extension of I into S, where we have the following C algebra map from R into S, where you send the variable Xij to the product of Yij and Cij. So we say that J is the standard standardization of I. Why would you care about this standardization process? So we show that I and J have the same graded dirty number. So the information in the pre-resolution of I, the minimal one and the one of J will be the same. And then of course, because you can read them from a free resolution, the K polynomial of R mod I will be equal to the K polynomial of S mod J, and the multi-degree polynomial of R mod I will be equal to the multi-degree polynomial of S mod J. Okay, so you give me any ideal here, and then you will capture the same homological properties of the original ideal. And now you are in a true multigraded setting that corresponds, yeah?
Is this Hartshorne polarization, is that related all to polarization for stable or Lorentzian polynomials?
Oh, no. In the paper of Lorentzian papers, there is a polarization, but it's not the same as this one. So the one in that paper will be, you take that one, but then you act also with a symmetric group, so it will be something symmetric again. Am I saying the truth?
It doesn't send monomials to monomials. It sends monomials to monomials in elementary symmetric polynomials.
Yeah.
But this one breaks symmetry.
This one is, but this one respects homological properties because basically that substitution is basically taking molding out by a regular sequence. That's it. And here our proof is the same thing. We can show that the substitution is basically the molding out by a regular sequence. Yes?
Well, this is not exactly work. Why does x1 squared go to x11 times x22?
I think it's x1, 2.
X1, 2.
Oh, okay. I see.
It's X1, 2. Oh, my writing is horrible, sorry. 1, 2. 1, 1. 2, 1. 2, 1, and 2, 2. Is it clear now?
Yeah.
So right from the beginning of our talk, we saw that being irreducible or being prime is something really important, but this operation, if the ideal has a variable, it clearly won't be a prime ideal, the thing that you get, no? So then the third part is that if I is prime contains no variable, then this standardization is prime. So this third part is some sort of algebraic, very algebraic Bertini theorem. Okay. Maybe I should say that this version of the theorem was done before with my co-authors Federico, Jonathan, and Fateme, but we also had here the assumption that I had to be called Macaulay. And for the case of Schubert, double Schubert polynomials was enough because matrix Schubert varieties are called Macaulay. Okay. So then I think that I can give a general idea of our main result, yeah? How the proof goes. So our main result was that this thing, sorry for the notation, so changing the signs is a covolume polynomial. So sketch of the proof would be, so you start you start with some irreducible T equivariant invariant varieties inside here, the product inside this space of matrices. Well, using Knutsson-Miller, so you get the prime inside R, such that this class is the multi-degree polynomial with T and then minus S. And now here we use this standard distinction. Well, not here. So then we get Q inside S, and now I'm putting here in quotations that it will be a prime ideal because we need to be able to handle the variables. But that's a technicality, so you can basically mod out the variables in some way, and then you get a prime ideal. Now inside a standard graded polynomial ring, and well, then you are considering the multi-degree polynomial of Q TS. By this item will be what we want to study, and these almost for free will be a covolume polynomial. So I'm putting here quotations because it might be the case that that prime is irrelevant. So then you might need to add some variables or do some tricks so that you can make that prime a relevant prime, and then it's really the cohomological class of some multi-projective variety. Okay, so that's the whole idea. So just as in Harrison's story, our main trick is being able to have a really silly trick called this standardization process. So then a priori, whatever you can do for, I don't know, Schubert polynomials, via this thing you will be able to do it for double Schubert polynomials. If you can do it for Grothendieck polynomials, then you will be able also to do it for double Grothendieck polynomials. Okay? And okay. Is there any questions? Yes.
For Grothendieck and double Grothendieck, do we know the M convexity? Do we know?
No, very little is known. So if the Schubert polynomial is 0, 1, we know that that the Grothendieck polynomial will have the N convexity. That's something that I did with Jonathan and Federico. And if we know that the Schubert polynomial is 0, 1, the matrix Schubert variety, one of the projections is birational, then by work of Eur and Larson, we know that then the Grothendieck polynomial will be Lorentzian. Very little is known. So I have something like 5 minutes. So I said something that this will be time permitting. So apparently I don't have time. So the idea is that if you have some Artinian braided algebra, let's say over C, then you have that the following are equivalent. So it's a very general theorem that R is Gorenstein. So there are many definitions of Gorenstein. So probably the most conceptual one is that the ring has a finite injective dimension over itself. And if it has finite dimension, then it's equal to the dimension. So an Artinian algebra is Gorenstein if it's an injective module over itself. Okay. So the other one is that R has Poincaré duality, and yet another one, R will be isomorphic to, let's say, a polynomial ring, a bunch of variables over the annihilator of just one polynomial that people call Macaulay dual generator, where GR will be a polynomial, let's say, in a bunch of variables y1 until Yn and xi, so r over this polynomial as differentiation. Okay, so this is a long story, and what we did here, generic Macaulay inverse system is something relative. So instead of taking r, so you can think of this as something going of r over z. So you then, what we did was you take any Artinian ring and you take a finite graded algebra over A, and then you can define when this morphism is Gorenstein. So the morphism is Gorenstein if it's flat and all the fibers are Gorenstein rings. You can define Poincare duality there, and you can define a generic Macaulay inverse system there also. It turns out that the three things there are not equivalent. The most general one is Poincare duality implies the other ones. But for instance, if you have nice rings, like a polynomial ring, so in a ring where every finally generated projective module is free, then the three are equivalent. So whenever you have a type of Quillen-Suslin theorem, the three ones are equivalent. Now, of course, our interest was studying the cohomology ring of complex projective variety over the integers. Okay, and I think I'm done with it. Yes, thank you.
Let's ask questions.
Can you say a bit about why 3 is true?
Why 3 is true? So it's actually an exercise in Eisenbuch's book. So it's a tricky algebraic argument, but it's basically when you are deleting and then you're deleting by variable. So let's say 1 minus a non-zero divisor and then a variable, then everything will become affine. So it's actually a very tricky argument. In the original paper that I had with Federico and Jonathan, we were also assuming that I was Cohen-Macaulay. We could not, but then apparently many things are in the book of Eisenbuch. Yeah.
Where in that book?
It's in the middle, like chapter 13 or something. Yeah. Yeah, it's a thick book.
Is there anything else you can say about the sort of evidence you have for the ACM part of the your ACM conjecture?
We did many examples.
What nature are those examples? Where did you get examples?
So our first one is by the result of Schum, that with ACM is enough, just in the biprojective case. And also, so actually, not just, maybe I can say more, yeah. So, if you have X inside this product of projective spaces, and let's just take that X is irreducible. So then let's say vector N will be inside the support of the, let's write it like this, the multi-degree of X here will be if and only if for all J inside N, the summation of Nj, where J is inside J, is smaller or equal than the dimension of projecting into the corresponding subset of products of projective spaces of X. Okay, so I have tried many times, and just with ACM, I believe this should be true. And This is true when X is irreducible, and voila, what the only difference that we really have is that because of the irreducibility, this type of function will be a rank function, will be actually a algebraic polymatroid. But as soon as you only have ACM, I think this also should be true. And we have examples of ACM where it's SMP, but not polymatroid. But the polymatroid thing is only dropping because this is not irreducible. So that's my whole guess. So there are, like, if you follow like Schum's result, I mean, there are many technicalities, but in the bigraded case, it works. And that's like the multi-degree support, the support of the cohomology. We know it should be there. And the only thing where the polymatroid comes is from the reducibility, because we know that this will be like, will be rank functions. Yeah.
How is the third part related to the rest of the paper?
Oh, I don't know. It's two things that I like.
Oh, I see. It's in the same paper.
It's in the same paper. Yeah. Cohomology rings, yeah. Yes.
So you have the standardization trick that the way you formulated it is for this sort of specific polynomial ring with this specific rating. Do you expect that this is really the only place that this sort of thing works, or is there a?
No, it works for any positive rating.
Any, oh, okay.
So I don't know if let's suppose that some variable xi has a degree 3,2, and let's say inside C2, then you will be mapping xi by some variables. I don't know, maybe y1, y2, y3, c1, and c2, where the degree of yi it's 1, 0, and the degree of ci it's 0, 1. For any positive rating, it will work. It's very general. But I'm just using the space of matrices because of the interest.
Any other questions? Otherwise, let's thank Yairon again.